All right, so here's where we left off last time. Earlier we were talking about how the integral of the function corresponding to that series will tell us whether or not the actual series, the series itself is convergent. Again, under the condition that that function is continuous, positive, and decreasing. Now, I assume you guys saw what I did to actually get the function that I'm talking about. Remember that a series is actually just a sum of a bunch of points. So like in this problem up here where it was 1 over the square root of n, we look at a function 1 over the square root of x and integrate over that whole curve, but we start at 1 and then go to infinity. Same thing was true up here, right? When the series was 1 over n squared, we looked at the function 1 over x squared, and we're going to integrate from 1 to infinity 1 over x squared. It actually turns out the bottom number in that limit, the 1, doesn't matter at all in this process, because it's what happens at infinity that really matters. Whether or not as we go out to infinity does this thing grow forever. So whether I put a 1 down here or a 4 down here or a billion down here, they'll still behave similarly. And that's what this theorem basically tells us, is that if it's positive and decreasing, then the integral and the series behave the same. So let's do one. Let's do this test for series right here. Now, my first... Oh, absolutely, I'm sorry. I'm running, but I forgot to click the button. So, in this case, let's think of the function f of x is, now in our case the function is going to be 1 over x squared plus 1. So we need to ask, is it continuous, is it positive, and is it decreasing as x goes to infinity? So first of all, is that a continuous function? Almost everything we work with is. Yes. In this case it is, because, I mean, with a rational function, they're continuous everywhere they're defined. Now this guy, if you think about where could he possibly be undefined, it'd be where the denominator was 0, and x squared plus 1 can never be 0. So this thing's continuous everywhere. So continuous, yes. Is it always positive? Yes. Squared plus 1. Got to be positive, right? Is it decreasing? No. Oh, yeah. As I go left to right, as I plug in bigger numbers for x, the denominator gets bigger, so the whole thing gets smaller. So it's continuous, positive, decreasing. Now there's two ways to check if something is decreasing. One is to graph it and just look at it, which is to me the same as what we're reasoning in our head, that this thing is going to get bigger on bottom as the whole thing then gets smaller. You can also take the derivative of something to find out if it's decreasing. If something is decreasing, what's true about the derivative? If something is decreasing, meaning going downhill, right? What's true about the derivative everywhere?
Negative. It's always positive.
So derivative means slope of the tangent, right? So if I'm going downhill everywhere, the slope is always downhill, which means it's negative. So you can test something to be decreasing by checking whether or not its derivative is negative. So if the derivative is negative, that's another way to do that. You might jot that off to the side here, but I don't need to do that here because I can tell by looking. So you can also graph these things. So because it's continuous, positive, decreasing, we're going to use the integral test. Which means all I got to do is find the integral, and if it converges, then this series converges. If it diverges, then this series diverges.
It diverges if it goes to 0, right?
No, if it goes to any number, it's convergent. If it goes to infinity, or it doesn't exist, or it goes to negative infinity, then it diverges. So diverges means doesn't go to a number. But 0 is a number. So, but again, I'm not looking at, maybe you're mixing up in your head the test for divergence with the integral test. Right? The test for divergence says, look just at this, ignore the sum, and say, does that go to 0? If the answer is yes, then we know nothing. If the answer is no, you're done and it diverges. Right? So 1 over n squared plus 1, what happens to that as n goes to infinity? It goes to 0. It's Bobo, right? Bigger, the exponent's bigger on bottom. Bigger on bottom goes to 0. Bobo. Okay? By the way, this is the first time I've ever taught Bobo, Baden, each DC. I learned that from my wife who teaches high school calculus, so she has all the little tricks to remember that kind of stuff. I just remember that the bottom's blowing up, the whole fraction has to go to 0. So since that goes to 0, the test for divergence fails. You might, if you want to write that down, test for divergence fails since a sub n goes to 0, right? It's only if it doesn't go to 0 that you know it diverges. So that's why I'm moving on now to the integral test. It's continuous, it's positive, it's decreasing. So we're going to find the integral from 1 to infinity of 1 over x squared plus 1 dx. Okay, so what's the first thing you do when you have an improper integral and you want to integrate it? Not split.
You want to change the infinity to t, so it's 1 to t. Oh, the limit.
Yeah, you rewrite as a limit. That's exactly right. This is, man, when did we do that? Probably like 7.8. I'll come back there. Yeah, there it is. Improper integrals, whenever you got infinities up there, you rewrite it as a limit like this. I know that's been a long time, but that's something you're going to have to remember to do, and it's nice that we're coming back to it. So let's go back to where we were. I'm going to rewrite this as the limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus 1 dx. All right, I'm going to grab my reference pages. I'm going to see if I've got a shortcut for 1 over x squared plus 1 on my integrals. I'm actually pretending to look this up because I already know the answer, but this is what you would do, right? Pull out your reference pages. And I'm looking for 1 over x squared plus 1 somewhere on my integrals. Do you have your reference pages? Have you already lost them? It's number 17 on page 6. It's 1 over a squared plus u squared. It's actually also a derivative formula for the inverse tangent, right? If you remember the derivative of the inverse tangent, you know this integral. This turns out to be right here. The integral is arctangent. I look it up, pull it out, whatever, of my derivative tables, my integral tables. This becomes the limit as t goes to infinity of, now the integral of this is inverse tangent of x from 1 up to t. All right, so we found the integral. Now let's actually take the limit. Actually, what do we got to do first? Do what?
You gotta change your x, right?
What do you mean change it?
taking the limit of t approaches infinity.
Well, before we take the limit, I need to do something else. I found that the integral, the antiderivative of this is tangent inverse, and it goes from 1 to t. So what do I do before I do the limit?
You change your endpoint?
No, not substituting, so I don't need to change my endpoints. You plug them in.
Oh, that's all your.
Yeah.
I was looking for something.
Something complicated? No.
Yeah.
Next step is plug in your limits. Top one minus bottom one. Sorry, was the question too easy? That was the problem. Limit t goes to infinity of tangent inverse of t minus tangent inverse of 1. Everyone's least favorite game. Guess what the professor is thinking. Okay. By the way, do you know what tangent inverse of 1 is? What angle, when you take its tangent, gives you 1? Pi over 4. Okay, so here's what I've got. I've got the limit. T goes to infinity. And by the way, you could look up 1 on your table and find the angle for tangent on your reference pages. Tangent inverse of t minus pi over 4. Okay, now the question is, what's that limit? What's the limit as t goes to infinity of tangent inverse? Picture of it on these pages. On page 3, you get the picture of the arctangent or inverse tangent. Looks like this. So, as t goes to infinity, as I go out this way, it's approaching whatever that height is. You might remember what that height is? Or do I? I'm just going to have to tell you. It's pi over 2. It comes from the fact that, whenever this is tangent inverse of x. When you graph tangent of x, it's got these asymptotes at negative pi over 2 and positive pi over 2. Right? And then to get an inverse, you reflect it about the y equals x line. So this becomes pi over 2 minus pi over 4, which is pi over 4. Because this is 2 pi over 4 minus pi over 4, or pi over 4. So what does that mean? Okay, it means the series converges. Okay, because the integral converges, the series converges.
So that's what you're talking about, how we can figure out whether it converges, but we really don't know what.
You don't know what it converges to. This pi over 4 doesn't tell us if this converges to pi over 4, something bigger than it, something smaller than it. All that we do know is that it converges. And in many cases, that's all we really need to know. Okay. So, set up the integral. Take the integral. If it goes to a number, it converges. If it doesn't, it diverges. Okay. Let's move on and look at the next example that I've got here, which is, it's actually a bunch of series in one. We've talked about the series, the sum 1 over n squared earlier in this section. And we also talked about the series 1 over the square root of n, which, by the way, is the same thing as the series 1 over n to the 1/2. In the last section, I talked about the series 1 over n, which is 1 over n to the first. Notice how all three of these, this one, and this one, are special cases of this series. That just means up here, p is 2, here, p is 1/2, and here, p is 1. It turns out that we can use the integral test to show that this converges for certain values of p and diverges for other values of p. The p-test, in fact, this is what's going to be later referred to as the p-test, is going to be anytime I've got something 1 over n to the p, I can tell immediately whether or not it converges or diverges by just looking at the p. So let's use what we know so far about series to find the values of p where this series converges or diverges. Okay? Now, first of all, before I actually use the integral test, let me point out that if p is negative, I don't even need the integral test to do anything. Let me show you what I mean. Think about if p is negative right here. Like, say this was 1 over n to the minus 1, or 1 over n to the minus 2, or 1 over n to the minus 3. Right? A negative exponent means to do what to it? It's 1 over, but if it's in the denominator, it goes up to the top, right? So an n to the minus 1 down on the bottom would be an n to the first on top. Okay? And in fact, if you think of 1 over n to the p, leave a space right here, I'm going to write the limit in there in just a second. That looks like n to the absolute value of p if p is negative, right? So if p is a minus 1, p is a minus 2, p is a minus 3, you just bring it up to the top, and it's now just n to that p positive. So the limit as n goes to infinity of 1 over n to the p becomes the limit as n goes to infinity of n to some positive power. Now, if you take the integers, positive integers, raise them to a positive power, they get bigger and bigger and bigger. Like 1 squared, 2 squared, 3 squared, 4 squared. As the base is getting bigger, the whole thing goes to infinity. Okay, so if p, the exponent, is negative, then the limit of the terms goes to infinity. What does that tell you about the series? If the terms of the series go to infinity, can you tell me if this converges or diverges? Diverges. Why? What test?
You just said it. You said if it goes.
If the terms go to infinity, Austin says it diverges, but why? What's the test that we're applying? I didn't take any integrals. Test for divergence. It's the one we just talked about. If the terms don't go to 0, then it diverges. Okay? So then it diverges by the test for divergence. That's why it diverges. Because it doesn't go to 0. By the way, if p is equal to 0, let's think about that case. What does this series look like when p is 0? It's just 1, right? It looks like the sum from n equals 1 to infinity of 1, right? And by the way, that means the limit as n goes to infinity of 1 over n to the p is just the limit as n goes to infinity of 1. And what's the limit of 1? It's 1. So then, what does that tell you? What has to be true for it to converge?
0.
It has to go to 0. This doesn't go to 0. Therefore, diverges. Anytime the terms do not go to 0, you know it diverges. Okay, so now let's talk about p as positive. This is where I'm going to use the integral test. So I'm going to take the integral from 1 to infinity of 1 over x to the p power dx. All right. Now this is actually the same thing as 1 to infinity of x to the minus p, right? dx. Which is then the limit as t goes to infinity. I'm just rewriting as a limit like we did before. 1 to t, x to the minus p dx. All right, now there's two possible outcomes to this. When you integrate x to the minus p, normally all you do is take and add 1 to the exponent and divide by it, right? So I'd get the limit t goes to infinity of x to the minus p plus 1 over minus p plus 1. Sorry, I'm going to run out of space here. We might have to move to the back here. But still, that's from 1 up to t. That's a plus right there. Now, why are there two cases where there's one value of p for which this is a problem? Right? It's not true when it's x to the minus 1. So this is when p is not 1. So if p is 1, then I'll have the limit t goes to infinity of, and what's the integral of x to the minus 1? Yeah, it's natural log of x. So 1 to t. All right, so let's plug those in. This up here becomes, I'm going to plug in my limits. So it's still the limit t goes to infinity of t to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus, or 1 over negative p plus 1 on the bottom. The bottom one down here is just the limit t goes to infinity, the log of t minus the log of 1. Now the bottom one right here is easy. First of all, log of 1 is just 0. But what happens to the log of t as t goes to infinity? The log function as you go out to the right. You don't have to draw this, but it looks something like this. What's it doing as you go out to infinity? It looks like it's leveling off, but it actually never does. It goes up forever. This is infinity. So that tells you right away, if p is 1, it diverges. Now what's happening up here is actually two different things. You've got, essentially, this constant right here is insignificant. The denominator down here is insignificant. What you really care about on this guy is what's happening right here. You are taking the value t and raising it to a power. And you're letting the base get bigger and bigger and bigger, go to infinity. Okay? Now, if the power up here is positive, then this thing's going to grow forever and be infinite. If the exponent is negative, then it goes downhill and goes to 0. It all depends on what's happening up here. Okay? So when is this positive? When is negative p plus 1 a positive number? Well, you're essentially doing 1 minus p, right? Minus p plus 1. When is that positive? When p is smaller than 1. So if p is smaller than 1, we get infinity. And when p is greater than 1, this is negative up here, we get 0. So I'm sorry that took more space than was there. I got to cheat and go off the side of my page. But here's, we know several things now. We know up here that if p is negative, it diverges. If p is 0, it diverges. If p is less than 1, it diverges. And if p is equal to 1. Notice all these cases where we get divergence. Negative, 0, less than 1, and 1. So everything up to 1 gives us divergent. Where is the only place where I converge to a number? When p is greater than 1. So now we have essentially all the information we need to make a final conclusion. Right? If you have this series right here, namely this one, it converges if p is greater than 1 and diverges everywhere else, so p less than or equal to 1. Now that theorem, that statement, all comes from test for divergence and integral test. We actually don't have to apply the integral test in the future. We have now a fourth test, geometric test for divergence, integral test. We now have something that I'm going to call the p-test. And that's when you have a 1 over n to the p, If p is bigger than 1, it converges. If p is less than or equal to 1, it diverges. All right, so immediately you can look at these two series and not have to do any work at all and tell me if they converge or diverge. This one is the sum from n equals 1 to infinity of 1 over n cubed. Converge or diverge? Converges by the p-test. Because p is 3, which is greater than 1. What about this one? Diverges by the p-test. Because p is 1/3, which is less than or equal to 1. So it diverges. So again, if you add up the terms of this sequence, as you keep adding terms, this gets bigger and bigger forever. Notice how this is consistent with what we saw earlier in this note, in the notes, right? 1 over square root of n is the same thing as 1 over n to what power? 1/2. Does that converge or diverge? Diverge, which is exactly what we saw happening here, but now we have proof. What about this one? Converge or diverge? Converge because it's p equals 2, and it's consistent. That's exactly what we saw happening here. Again, we don't know what it converges to. We just know now that it does converge. But that's what we want to know. It's very important for us to know that. At the very beginning of class at 9 this morning, we introduced something called the Harmonic Series, which was this one. Right? That's 1 plus 1/2 plus 1/3 plus 1/4 plus and so on. By the p-test, what do you know? Diverge or converge?
Less than or diverge.
It's or equal to, so diverges. Because p is equal to 1. It's interesting to me to note that you've got a very interesting behavior occurring near p equals 1. I'm going to throw this in here. Note. When p is equal to 1 into the first, this thing will grow forever. In fact, if you pick a very large positive number, I can take enough terms of this series and it will be bigger than any number that you pick. Eventually, it gets bigger than any number. So this thing grows forever. Like the logarithm, it's slow, but it will still get as high as you want it to if you go far enough out. On the other hand, something as close to 1 as I can make it just by writing it. Let's say I have 1 over n to the 1.000000. You pick how many zeros you want in here. 1 to that power. 1 over n to that power. What is true about that series? It converges because it's greater than 1. Even though it's really, really close to 1 over n, its power is slightly higher. We've just mathematically proven that that one will converge. Even though this one up here diverges. Think about it. How close is 1 over 1 to 1 over 1 to the 1.00000001? 1 over 2 to 1 over 2 to the 1.00. Those are really, really close numbers. Except this series down here will eventually level out and never go higher than some number. It converges to some number. But this one up here grows forever. I think that's pretty cool. Fascinating. So let's kind of back up to the point that we made earlier. That again, it's a little bit uncomfortable to realize we can know a property of a series. We can know whether it converges or diverges without knowing what it converges or what it converges to. We can know if it converges without knowing what it converges to. But interestingly, we can actually approximate what it converges to without knowing exactly what it converges to. And that's what this section right here is talking about. We can estimate what the sum of the series is. So suppose we've been able to use the integral test to show that a series a sub n converges. We now want to find an approximation to the sum s of that series. So remember that any partial sum is an approximation to that. If you just add the first 10 terms, that's an approximate value of the series. If you add the first 100. Like back up at the top whenever I had those tables, right? This is an approximation. Actually, because this one diverges, it's a bad example. This 1.6447 is an approximate value of this series, even though I don't know what it is exactly. But it's not exact. The question is, how close do I know that I am? And that question is the question of a numerical analyst. That's the question that we, in the applied mathematics world, often ask is, yes, we can approximate it, but how close are we? And using the actual integral test, we can show that we can find out how close we are. Like, are we plus or minus in the 6 decimal place? Are we within 7 decimal places? How close are we? So to find out, what we need to do is estimate the size of the remainder. And remember that what I mean by this S right here, S is the whole sum from n equals 1 to infinity of a sub n. And this S sub n is like the sum from I equals 1 up to n of a sub n. How close is this to this? We know that as n goes to infinity, Sn approaches S, but if I stop short, how close am I? What I really want to measure is S minus S sub n. Okay? So, do that. What this looks like is the following. It's A1 plus A2 plus A3 plus all the way out to A sub n plus A sub n plus 1 plus A sub n plus 2 plus dot dot dot. There's your S. It's the whole thing. Now S sub n is A sub 1 plus A sub 2 plus all the way out to A sub n, and you stop. Right, so S is this whole thing right here. S is all of this. And S of n is the first n terms. Now, look at those, and what do you see happening? You've got an A sub 1 minus an A sub 1, right? Cancel. A sub 2, A sub 2, A sub 3 cancels all the way out to A sub n. What are you left with? Yeah, that's what's called the tail of the series. So your remainder is what's left over at the end. And this R sub n is the error made when you use S sub n, the sum of the first n terms, as an approximation for the total sum. Now I'm going to use the same notation and ideas that we did in the integral test and assume that f is decreasing starting at n. So imagine this blue curve right here is your f of x. And since this is like n plus 1, then the height to the curve, that right there is your a sub n plus 1. So the area of this box, which is 1 this way and a sub n plus 1 this way, is a sub n plus 1. Your area of this box will be a sub n plus 2. The area of this box is a sub n plus 3. So your remainder is the boxes. And because f is decreasing, how does the area of the boxes compare to the area under the curve f? Well, if you do the integral starting here and do the integral from n to infinity of f of x dx, notice you've got all this extra space in here, so this area is bigger than the boxes. Agreed? And then the same thing is true if I start my integral here at n plus 1. Notice how the size of these boxes, instead of going to the left and drawing a box, I start at a sub n plus 1 and go to the right and draw a box. Notice that this is also, oh, I want to do this in blue again. This here are the boxes in this picture, because again the area is starting at n plus 1 but going to the right now, so we're using left-hand rectangles instead of right-hand rectangles. And now, how does the integral that starts at n plus 1 and goes to infinity of f of x dx compare to the area of the boxes? Well, you've got excess, right? So the area of the boxes is bigger than or equal to the area from n plus 1. Area under curve here. Which is where you get this theorem right here that says that the remainder, that is how far away you are, your actual error, is somewhere between the integral from n to infinity of f of x and n plus 1 to infinity of f of x. So this will give you a way to bound the error. You can find out just how far away you are from the actual solution, the actual series. Now let me show you an example of that in practice with this next one. And this will be the last example we do. In fact, I'll probably save 1.4. I'll go ahead and save that for Wednesday. We'll stop with this example right here. Let's use this estimate theorem right here, this number 2, to approximate the series and find out what the error is in this approximation. So again, just looking at this formula, the remainder, that's your error, is somewhere less than or equal to the integral from n to infinity, but bigger than n plus 1. Usually, we only use this part of it right here. In this example, that's all I really have to use. I want an upper bound on my error. Okay. So let's do this series right here, 1 over n cubed. And I want to approximate the actual sum from n equals 1 to infinity by using just the first 10 terms. What's the notation I use to write the sum of the first n, or in this case, 10 terms? How do I denote that? What have I been using for notation for the sum of the first 10 terms? What'd you say? A sub 10 is actually the 10th term, not the sum of the first 10 terms. I want like A1 plus A2 plus all the way out to A10. What's the variable I use for that? I'm fishing for this right here. This guy right there. S sub n stands for partial sum. So in this case, I'm looking at S sub 10. This is part A. Now, S sub 10 means, for this series, 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed. And go ahead and write them all the way out. And in your homework, you'll need to go ahead and be able to calculate this with your calculator. And get a decimal number. So when I plugged this into my calculator, I got 1.1975, and it kept going, but I rounded to the 4th decimal place. The question is, how close is this to the full n equal 1 to infinity of 1 over n cubed, right? We don't know what that equals. But we know it's going to be close, but how close? I mean, is it possible that s is like 2 and I just haven't got there yet? Is it 20 and I haven't got there yet? Or is it 1.2 something, 1.19? How close am I? And so that's this question right here. Estimate the error involved in this approximation. How far away is this possibly from the actual value of the series? So now we're going to use R sub n as my notation. I'm going to use the fact that R sub n is less than or equal to this formula up here. The integral from n to infinity of f of x. What's my f of x in this case? It's 1 over n cubed, but I'm going to use the variable x because I'm talking functions now. So 1 over dx, or integral from n to infinity of x to the minus 3 dx. Now I'm actually going to use R10, but because the next question is asking me about how many terms I would need, I'm going to do this for n and then plug in my 10 at the end. So let's take this integral. First thing you do, always rewrite it as a limit. Okay, so the integral here no, only natural log if it's 1 over x. How do you integrate x to a power? Add 1. Not 3. Now you add 1 and then divide by that. Negative 2. Add 1 and divide by it. From now n to t. So, by the way, I'm going to rewrite this as, I think it's negative 1 over 2x squared. That makes it a little easier to plug in my limits. It becomes negative 1 over 2t squared minus a minus. I'm plugging in the limits now, by the way. 1 over 2n squared. Right, plug in t into this. And I get negative 1 over 2t squared minus, and then plug in n. This minus and this minus makes it a plus 1 over 2n squared. Now, what variable am I taking the limit with respect to? T. So this one depends on the t. What happens to this as t gets big? Goes to 0. Now this one doesn't depend on t. So don't get fooled and think it goes to 0 because there's an n squared on bottom. This is fixed, right? You're only taking the limit as t goes to infinity. So what you end up with is just 1 over 2 n squared. Whatever n is here, that's what you get for your Rn. Rn is less than or equal to this. That's what we just proved, that the remainder is no bigger than 1 over 2 n squared. So what's the upper bound for the remainder when I do the first 10 terms? It's less than or equal to 1 over 2 times 10 squared, or 1 over 200. Which, by the way, is 0.005. So by the way, what that tells me is this. The actual sum could be written as 1.1975 plus or minus 0.005. The remainder is no bigger than that. That is, the distance between s and n is no bigger than that. So 1.1975 plus 0.005 means I could go up to as big as 1.202, something like that. But it's never going to get bigger than that. I know my series isn't bigger than that. All right. Now, what's the second question? Part B asks.
How many terms are
If we want the sum to be within 0.0005, how many terms do I need to add up? How would you solve that? Any ideas for that?
Could you set it equal to 1 over 2 n squared?
Since Rn is less than or equal to 1 over 2n squared, you want Rn to be less than what? This 0.005? 0.0005? So yeah, I think if you set that equal to 0.0005, and then do what? I'm setting, because that was the question, I want it accurate to that distance. The question is, how big does n have to be? Actually, even better, I want this Rn to be less than that. So I'm going to solve for n there, right? So I got 1 over 2n squared less than 0.0005. So what I would do is divide both sides by 0.005. And maybe multiply both sides by n squared. That gives me 1 over 2 times 0.0005 is less than n squared. So that's 1 over 0.001. Over 0.001. That's 1,000th, so that's 1,000. And then square root both sides. N has to be bigger than, what's the square root of 1,000? 31.6. Okay, so how many terms do I need? 32 terms. If I go 32 terms, I know I'm within 0.0005 of that sum. And that's how we'd answer that question.